Hi, I'm Saavik Ford.
And I'm Barry McKernan.
And we're going to talk to you today about black holes. So we've been asked to start with a little bit of introduction on what is a black hole. So I want you to think for a moment about this box that I am going to toss up here from the surface of the Earth. Okay.
Good catch.
So, what just happened?
It went up and then it came down.
Okay, so when it went up, what happened when it came down?
Well, it slowed down and then it stopped going up and then it started to come down and it speeded up as it came down.
Okay, cool. So what would happen if I tossed this up at a faster speed?
It's going to go further, but it's still going to slow down, turn around, and then come back down.
All right, let's try it.
Try it, yeah. Another
higher?
good catch. Awesome.
Okay.
Yeah.
What if I threw it really, 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 really fast? Like, let's just say 100,000 miles an hour.
100,000 miles an hour. Well, we would do serious damage to the museum ceilings. We don't want to do that. But let's imagine there were no ceilings here. Then it would go super fast that way. Because it's made of plastic, it would suffer severe damage and probably melt. But let's assume that it could go through the atmosphere. It would go all the way out into space, assuming that's indestructible.
Would it ever come back?
At 100,000 miles per hour, no.
Oh, why?
Because it's moving so fast that the pull that's trying to bring it back this way isn't strong enough to bring it back. So it can escape.
Oh, okay. So that's faster than the escape speed of the Earth.
That's right.
Okay. So could I make the escape speed of the Earth bigger?
It would be really, really difficult. But yeah, you could in principle if you squashed the Earth. Okay, so not that difficult. Just take the Earth and kind of squeeze it together so that everything on the surface of the Earth is closer to its center. And then the Earth would be denser, more compact, and would have a stronger pull from the surface.
Okay. So then the escape speed at the surface would be bigger than it is now.
That's right, yes.
And what if I kept going and squashed it and squashed it and squashed it and squashed it and squashed it?
Then the escape speed would keep going up.
And what happens when the escape speed gets to be the speed of light?
Okay, well then you would need to throw something away from the squashed Earth faster than the speed of light. But wait a minute, that's a problem.
Right. So then we're going to have a thing that can't emit light, and it's got an incredibly strong gravitational pull.
So if I'm in space and I'm watching you squish the Earth and everyone on Earth is screaming, going, "Oh, why are you squishing the Earth?" And it's getting really nasty and hot and molten and all the rest, and the escape speed from the surface is increasing. Eventually, I'm going to get to a point where the escape speed reaches the speed of light and then goes beyond the speed of light. So light trying to get away from the surface is going to go, it won't be able to get away.
So it'll be like this box when I go like that.
Yeah, light would behave just like this. So the squashed Earth that I'll see getting more compressed and molten and nasty and all the rest, eventually I won't be able to see it because light won't be able to get away. I've squashed something so much that light can't get away. The escape speed is too much.
So that's a black hole.
Sweet. Simple.
Cool.
How much would I need to squash the Earth to turn it into a black hole?
So you would need to make it so small that it would be, let's see, is the island of Manhattan small enough?
Yeah, way smaller.
Way
the Earth needs
smaller.
to be about the size of a grape.
Yes. So
That's difficult.
yes, it's very hard. So we're not going to do that.
Yeah.
All right.
Yay. So that's what a black hole is. So what do we work on?
So what do we work on? So we work on actually black holes that are much bigger than the Earth.
Yep.
So if we were to do that sort of evil thing, you know, the evil mad scientist, and crush the Earth to the size of a grape, it would be very bad for the people on Earth. But the moon would actually not care or notice.
But wait, I thought black holes suck.
No! You see, black holes go around, or sorry, the moon is going around the Earth in an orbit, and it's being pulled on by the Earth right now. And in that whole process of crushing the Earth down to the size of a grape, we did not change the mass of the Earth, and we did not change the distance from the Earth
From
to
the
the Moon.
center of the Earth to the center of the Moon.
Right.
Right.
And so the gravitational force didn't change. The Moon is still going at the same speed that it was, and so it is still going to continue to orbit quite happily, and it will not notice that the Earth has been turned into a black hole.
Wow. So black holes don't
Don't
suck.
suck.
Right.
We work on black holes that live in the centers of galaxies, and so a lot of people would think, oh my god, the galaxy is going to be swallowed by a giant black hole.
Nope.
But actually it's not, because the stars that are in the galaxy orbit far enough away and at the right speeds to not be sucked into a black hole, or falling into a black hole would be the more appropriate term. And
So how do we know this? What do we observe when we look at the center of our galaxy towards where we think the black hole lives? What makes us think there's a black hole there?
So we have stars in the center of our galaxy that are 10 times the mass of the sun. And they are going around something. They're being whipped around, and we can actually see them going in orbits that look just like planetary orbits around our sun. And there's nothing there.
So it's as if you saw planets. If you took our solar system and you made the sun go dark, but you could see planets kind of going around in these orbits going. So something is making these stars that are 10 times the mass of the sun change direction, speed up, slow down, speed up, slow down. And we can figure out, in the same way that the sun is way more massive than planets that go around it, and we can make them whip around, the sun can make the planets whip around. So you have to have something really massive to make stars that are 10 times the mass of the sun whip around them like they're nothing. So we can figure out that the black hole in the center of our galaxy is 4 million times the mass of our sun. And it makes stars behave like they're just little planets being flung around, which is pretty cool. We can watch that happen. And if you go on YouTube, we'll try and add a comment on the feed afterwards, a link to a YouTube video which shows you the stars doing that.
Astronomical observations.
Yep.
Actually, there's the black hole.
Yep.
Our galaxy, like most galaxies with black holes at their centers, are not emitting light. There's not a lot of light being emitted from the center of the galaxy. Black holes, of course, emit no light themselves.
Yep.
But if you had a lot of gas that was being delivered to a black hole, then the gas would be trying to cram into the black hole, and as it falls, it's going to get into a smaller and smaller space, rubbing up against other gas that's also trying to fall into the black hole. And so as it rubs up against the other gas, friction causes it to heat up, and the heat causes it to glow very brightly. And so in some galaxies, there are gas reservoirs that are feeding black holes in the centers of the galaxies. And those black holes, the material that's falling into the black hole is glowing very brightly. And it's in fact glowing more brightly than all the stars in the rest of the galaxy put together.
Yeah.
And so when we look out, we originally saw these galaxies, and we saw this bright point in the middle that looked like a star, but we could tell when we broke up its light into a rainbow spectrum that it was, in fact, not a regular normal star, and people started to call them something else, quasi-stellar objects, which got abbreviated to QSOs, or sometimes quasars if they emit in the radio wavelengths. And then we realized that they were actually enormous black holes at the centers of galaxies that were being fed by gas, and the gas was emitting light that we could see.
Yeah, so essentially, even though you can't see the black hole at the center directly, in the same way that you can't really, in a really good horror movie, you can't see the monster, but you can hear the screams of the people that are being chewed up by the monster. Essentially, by looking at active galactic nuclei, we can see stuff being torn and shredded by the monster that we can't see. So we figure out, there has to be a monster there because we hear a lot of screaming. Right.
A quick question from Jennifer Kingslake. She says, how do you measure mass from just looking at something or just from the light that's emitted?
So we don't necessarily measure it. There are indirect ways of measuring it from just the light. But in the case of, for example, the center of our own galaxy, the black hole there, it's very direct. So it's the same way that we measure the mass of the sun or the mass of the Earth or the mass of Jupiter. If you have an object in orbit around another object, then the speed that it goes at basically tells you a combination of the mass of the object that's pulling on it and the distance from that object. And so if we can measure the speed of the orbit, so we just have to watch the thing go around to measure the speed accurately, and then you measure the actual distance from the object to where it seems to be being pulled on from, then the only thing that you don't know is the mass of that object, and then you can figure it out.
Yep. Good question.
So how do you study black holes, and how is the study of black holes changing? How are we getting sort of better looks at them as the years go on?
Okay, so actually we've gotten some really exciting new tools to look at black holes just in the last year. There are many kinds of black holes. So there's the black holes that live in the centers of galaxies. And then there's also black holes that live in our own galaxy. For example, in Cygnus X1 has a black hole that we can see because it is destroying its partner. It's a binary. It was a binary star, so you have a black hole and a regular star, and they're going around. And the black hole and the regular star have changed their structure and distance in a way that allows the black hole to suck material off of the normal star.
Right, they're doing a dance of death. Essentially, the outer layers of the star are being stripped and feeding the monster. And so we can figure out what the monster is doing by watching the star being eaten alive.
And we think that stars like Cygnus, stars that end up as black holes like Cygnus X1, that they come originally from very massive stars that end their lives in supernovae and become and leave behind this remnant core that becomes a black hole. Those are called stellar mass black holes because they come from stars, as opposed to the supermassive kind that we study in the centers of galaxies. And last year, the LIGO team detected for the first time gravitational waves that came from the merger of two stellar mass black holes. And this was a very exciting type of discovery and a completely new way of looking at the universe, really. Up until last year, the way that astronomers knew about the universe was almost exclusively from the light that came to us. So we could look at what we saw, and then light would come to us and we could analyze it. And we have lots of tricks and ways of using that to get a greater understanding of our universe. But gravitational waves are a completely different type of wave, and people have made the analogy that it's like before we could see, but we could not hear, and now with gravitational waves, we can hear the universe. So gravitational waves come from, actually here, let me make one. See, I accelerated a mass. However, because gravity is a very weak force, I did not make a very strong gravitational wave, and no one has a hope of ever detecting that one. But if you have very large masses and that are very compact, like black holes, that are orbiting around each other, then they generate very strong gravitational waves that we now have incredibly sensitive detectors to detect. And we've basically, we're very excited to be able to use this new window on the universe to understand stellar mass black holes. And in the coming years, there are plans for similar gravitational wave detectors. LISA is basically the European and hopefully joint with NASA plan to do a space-based observatory that will let us look at supermassive black holes and their gravitational waves. So.
One of the big surprises from the LIGO result was that the very first gravitational wave detection came from two black holes that were overweight compared to the black holes that we see in our galaxy, the stellar mass black holes that we see in our galaxy. And everyone was kind of surprised by that. And it means we had to think about, well, how could you make two slightly overweight, actually significantly overweight stellar mass black holes close together and have them merge so that we could detect this. And we, in fact, we have a model that we're working on that explains the merger of these stellar mass black holes in terms of a swarm of black holes, small mass black holes, in the centers of galaxies around supermassive black holes. And so essentially, as Saavik said, if there's a gas disk around a supermassive black hole, There are also stars and small mass black holes also around this, the supermassive black hole in the centers of galaxies. Some of them will end up in the disk. There's so much massive gas in the disk that you will slam some of these small mass black holes together, and so you can quite quickly build up larger mass black holes. And so one of the things that we're really excited about over the next 2 years is we want to see if LIGO will detect more of these overweight stellar mass black hole mergers. If they do, it would suggest that some of these mergers happen around supermassive black holes in our universe. So that's super exciting.
And that's directly related to our research.
Yeah. So we work on that.
I want to jump in with a couple questions from our Facebook audience.
Yep.
From Abby Stoms, who asks, "Can a black hole die?"
Yes,
So
in principle.
we think that
Yeah.
a black hole can in fact die,
Yeah.
but not right now.
Have patience.
So basically, this is one of the things for which Stephen Hawking is most famous, is this idea called Hawking radiation. And it comes from the idea that if you have a black hole, that it can evaporate. And this comes from the idea that in our universe right now, in this room and everywhere where you are, your room, there are particles that are popping into and out of existence. And we have experimental evidence for this. There's an experiment you can do called the Casimir Effect that can detect these particles that pop in and out of existence. And this is totally legal as long as they pop in and pop out in a very short amount of time. The problem is that they're doing this in every cubic centimeter of the universe.
Including right here.
And also right around the edge of the event horizon of the black hole. And so we said, right, that a black hole is formed when the escape speed from the surface of an object gets bigger than the speed of light. So this effect where particles pop into and out of existence doesn't care that there is this surface. And so particles will pop into and out of existence perhaps across this surface. The problem is that the gravitational pull on one side is in and strong, and it's slightly less strong on the other side. So you could have this situation where a particle pair, and they always come in pairs, and that's why they pop out and they recombine, and they always do this as this pair. And as long as they pop out and recombine as a pair, that's legal.
But if one goes inside the horizon, the event horizon of the black hole, and the other is left outside,
they can't find
come
each
back.
other in the legal time
Yeah.
to make it all okay and conserve energy. And so what actually happens is something else has to conserve the energy that was spent to create the particle pair. And what is going to pay the bill is the mass of the black hole. So that particle that escapes carries away a fraction of the mass of the black hole. And
Basically the particles that pop into and out of existence are real only for a tiny, tiny fraction of a second. But if you've just taken one away, the other one can't annihilate with its partner. It's become real, it exists, it can no longer go away. It's real and it scoots off away from the black hole. So you have a stream of particles moving away from the black hole. So the black hole looks like it's emitting a whole bunch of particles. And the energy to make those particles real and stay real comes from the black hole. So the black hole is losing energy as it radiates the stream of particles away. So if there's nothing else feeding the black hole, and if you leave the black hole alone, eventually it's going to keep losing energy, it's going to shrink. It'll get smaller and smaller and smaller and smaller and smaller. And eventually it will explode in a flash. The problem is black holes have gravity. They can pull on a lot of material, and space isn't really that empty. And so there's enough radiation, there's enough mass, that these things will stay in existence until a very long time from now.
And in fact, even if you had a completely isolated black hole in the middle of nowhere, away from all matter in the universe, right now, the light that pervades the universe that is left over from the Big Bang is hot enough that any dying star that will produce a black hole, that black hole's mass is big enough that it will divert the light from the cosmic microwave background radiation, and it will prevent that black hole from evaporating. However, as time goes on, the universe is getting more and more spread out, and that radiation is decreasing in temperature. So eventually, the light will not be able to balance out even stellar mass black holes. So if you have very, very, very small black holes that we don't actually know how to make, like black holes the size of the Earth, those could have evaporated by now, but we don't see any evidence.
So
that
if
they
you're
exist.
a black hole and you're watching, it's okay. You've got lots of time.
Yeah.
I do not think we could wrap up on something more mind-bending than that. So I think that's where we're gonna leave this one.
Awesome.
Thank you guys so much for making time for us today.
Yeah, absolutely.
Sure.
Thank you.
Thank you.
Cool.